We have a previous video that describes a little bit more about the technology, but it's an optical profiler. It's analogous to a laser confocal microscope system, but our technology is a bit different. It employs what's called our Z-dot technology. Today, I'm going to talk a little bit more about one application area where we can look at transparent materials, in particular to microfluidics devices and looking at multi-surfaces. The sample that I have on here is kind of like a lab on a chip, so it's actually located here on the stage. And what I'm going to do is look at the different layers to be able to measure, even though it's sealed, the distance down to the bottom of the sample so that somebody can know what the height of the actual well or channel happens to be for their fluid dynamics, etc. So let's go ahead and do that measurement, Cameron. So I'm going to go ahead and adjust the system. Currently, we're looking at the top surface of the actual sample. When I employ our Z-dot technology, it allows me very easily to tell when I'm in focus on this particular surface. If I were to scan down to the next layer, the channel is actually located here. So this is the top surface of the channel that's coming into focus that you can actually see now. And then the actual channel bottom will be represented in this particular area. So I'll go ahead and move back up to the top. Let me set the ranges for the scan. So I'll do that by jumping into here. What we want to do is bracket or encapsulate the area in the Z direction. So doing so, what I'll do is I'll move above the surface so I can capture that. I'll simply hit this as top surface. Then I'll move to capture the top surface. Below that, we'll capture this region. And then I'll go down to that next layer, which is coming up. So at this point, the next layer, which is the air gap or the top of the channel, is in focus. So I want to make sure I capture that. So we'll do so by picking this as the top of the middle section. We'll make sure we capture the full top of the middle. So there's the bottom. And then we'll actually capture the bottom layer. So let's do that at this point. And then all the way through. So at this case, what we're going to do is collect or resolve 14 scans for the top, 13 for the middle, and then 12 for the bottom. Or let's go ahead and just increase that. So maybe I'll adjust this to something like 300, in which case it'll increase the slices. Let's go ahead and say OK. On our software interface, what it does now is it actually puts in the different layers for the scan. I simply need to come over here and say scan. It'll actually collect the data. It'll take roughly, in this case, probably about 15 seconds or less to capture the full 3D surface for each of these layers. And we'll have that information. So here is our channel. What I'm going to do is take out some of the information that we don't need to take a look at. So I'll go to the 3D analysis window. And in this mode, I can see these different layers. I'll actually look at our multi-surface software. I'll change the degree of opacity. And since this is solid material that I'm going into, I want to actually remove from the data set for the profile information the stuff that is not part of the channel. So I can do so as I've just done. I have filtered this information out. I'll do the same thing on the very bottom layer, which is now the bottom of that channel. So I'll bring this up, go ahead and filter this guy out, like so. Let's move this box out of the way so you can see the channel. So we'll just simply collect it kind of like that. Now, this is arbitrary in how I bring this up and display it, but let's say I want to go ahead and bring this into some degree, make the bottom 100% opaque, make the middle somewhere in the 80s, and then maybe the top layer, which is the very top of this plastic slide, somewhere up here. And we'll say okay. Let me go ahead and just close this down and eliminate that one. We'll look at that data set now that I've processed it, and what you'll notice is that per the cross section, I actually have 3 individual heights. I have a height from the top to the middle to the bottom. So if I look at this cursor set, it allows me to average all the information for the height that we've just collected in the Z-stack all the way in between. In this particular measurement, I have a distance from the top to this layer, which is layers 2 to 3. They're also color coded. That's basically 517 microns deep times its refractive index. The air gap is literally here in this center section. It is an roughly 81 micron channel depth. And so now I can actually see this. It is made out of plastic, so it's no problem collecting it. The color information that came back is the white light reflected color of the actual sample. Should I want to use false color to actually look at this, I can simply click on that value, based on the information that's present, I can change the color histogram or adjust my color scale based upon the information that I'm displaying, such like something like this, so I have a difference in the sample. But what's important is if I had multi-channels in here, depending on where this other cursor set is, not only can I look at the Z information down for differentials, I could look at the distance across based on this cursor set as well, and look from left to right, also with all of the Z information. And that's it.
So you can use that to calculate, you just did channel height effectively. You could use it to calculate channel volume using from a 3D map, presumably?
Correct. So you can measure basically length, width, and height. If it's an open channel, you can calculate the volume. On the channels, you can also calculate the roughness, so you can use that aspect. We also work with refractive index, or what are called sample compensation objectives, to account for the refractive index so that we can look at those. We can also look at wet channels. And even though this is a multi-surface software package that I'm referring to in channel measurements, we can look at photoresist, any transparent material. If the first two are transparent for the layers, I can actually look to the third, which can be opaque or also transparent. So any material where you want to know the height in that information that's not a step, and you have these channels or change in refractive index, you can differentiate those materials.
And the fact that you can see through, or you can measure like a sealed channel effectively, is that something that other instruments can't do?
It becomes more problematic on some of the other technologies. One typical measurement tool that people will have is what's called a stylus profiler. That's limited to only the top surface because the profiler cannot actually get down to the bottom layer. So the optical technique, as I'm showing, actually has huge advantages over that. Plus you're seeing a large field of view and the ability to see inside.
And what's the limit of resolution of this type of technique?
We can step at roughly 15 nanometers, but your resolution is going to really depend upon the thickness of the material and the degree of refraction due to its refractive index. And that's all going to refract, in which case sometimes you have to start moving up to the lower magnification, lower NA type objectives. But the limit's going to be the working distance and those components that I just mentioned for properties.